AP Chem. Today we're going to be talking about precipitation reactions. We're in solutions, so we're going to be kind of shifting gears and eventually talking about precipitation reactions and the stoichiometry that goes along with them. So first of all, we've got to talk about what you can expect when you mix two chemicals together, how you predict what you're going to get for your precipitate, and how to write those reactions out. So just as a gentle reminder for you, when you have a compound that is soluble and it's an ionic compound, those compounds are going to dissociate and dissolve and break apart 100%. So for instance, sodium hydroxide is a soluble ionic compound, and when I put that into water, it is going to break apart into its Na plus and its OH minus ions, okay? I'm going to go back for a second. When we want to talk about something being soluble, what we do is we write the phase AQ after it to represent that it's aqueous or it readily dissolves in water. In contrast, insoluble ionic compounds, what happens is they actually, I'm getting a little ahead of myself here. They will actually stay together. What happens in this case is that the attractive forces that hold that compound together hold it in a way that makes it not want to break apart. And there's a couple different interactions that are going on there. One of them is the Coulombic attractions between the ions. Another is the water trying to pull those apart, and whether or not the water, the energy benefit of being pulled apart is better. And then that plays into something called entropy, which we will talk about in a unit or two. So when we talk about insoluble compounds, basically what happens is the overall benefit of breaking apart does not balance out to how much effort it would make that happen. And so it doesn't. So if we have an insoluble compound, what we do is we write that is a solid when it's in solution because it's not dissolving. Now, when we talk about the rules and how to predict that, the most important part is going to be looking at the individual ions that make up our ionic compounds when we have these types of reactions. And when I go through these rules, what you have to think about is that the rules that I'm going to start with at the top are going to dominate over any other potential behaviors that you're going to see for ions. So the ranking of these orders is important because they're going to help us predict what's going to happen. So the first rule will beat out any rule about an ion below it, and so on and so forth. Okay, so here are our rules. When you look at an ionic compound, like I said, you want to pay attention to both the cation and the anion because there could be potential rules about all of them. And I would say when we start off with these, the anions are going to be a little bit less important than the cations to start off with. So when you look at your cations, which are your positive ions, you're going to look at them and you're going to look for the top two rules kind of up here. And then if you can find those, then you'll kind of be off to the races. And now that I'm thinking about it, there are some anions that are important here. So just, I guess, pay attention. Okay, so when you look at your compound, if you see a nitrate, which is NO3 minus in the compound, you see here are cations, the alkali metal ions. So those are going to be hydrogen, potassium, lithium, sodium, those guys in the first family in our periodic table. If you see the acetate polyatomic ion and the ammonium polyatomic ion, those are all going to be soluble. So if you look at those and you see them in a chemical formula and you see that they are there, those are going to be chemicals that are soluble. They will dissolve because of the presence of those particular ions in there. So again, the nitrates, alkali metals, including hydrogen, acetate, and ammonium, if you see them in a formula, it makes it soluble regardless of what else is in there. Okay? Moving on to our anions. If you have a chloride, a bromide, or an iodide salt, they generally will dissolve unless they are partnered with a heavy metal, and that would be silver, lead, and the mercury 2,2+ ion. So if you see a silver chloride, a lead chloride, or a mercury chloride, those are going to be insoluble and they will not dissolve. So that big metal that's attached to it will make it not able to dissolve. Okay, moving on. Most of your sulfates are soluble, so they are going to dissolve unless they are with barium, lead, the mercury 2 polyatomic ion, and calcium. So if you see a sulfate in a compound, it should dissolve unless it's partnered with one of those 4. Okay. Most of your hydroxides are not soluble, but there are 2 that are, and they are sodium hydroxide and potassium hydroxide. So those guys are going to be really readily soluble, and they dissolve a lot. Okay. The other ones do not dissolve very well when you put them into water, just because they kind of settle out as a solid instead. And most sulfide, so sulfide is going to be just S. Carbonate, chromate, and phosphate salts are insoluble. However, like I said, if you see a phosphate and it's partnered with something that has an alkali metal like sodium phosphate, that is going to be soluble because the rule about the alkali metals is further up, and that beats out the rule about the phosphates. So just be aware that the order is really important, and you're looking, if there's rules about 2 of them, look at their position to kind of predict what's going to happen. Okay, some precipitate colors, just kind of for your own information. We used to have to memorize these, but you don't anymore. The iodide precipitates tend to be kind of a yellowish color because iodine is kind of a yellowy browny color. Copper precipitates tend to be, for the most part, a bluish color, especially if they're copper 2+. If you have copper 1+, sometimes you get green. Your sulfides oftentimes turn kind of a blackish color. Your iron 3+ precipitates are going to be orange in color, and then a lot of the other ones tend to be white. Sometimes if you get a fun transition metal, you'll get a fun color for your precipitate as well. Okay, so those are your rules. What we have to do is we have to be able to look at a chemical reaction and predict what's going to happen when we mix 2 things together. So when we have those 2 things mixed together, potentially you could get what's called a precipitation reaction. If you recall, a precipitate is the solid that is generated from 2 chemicals reacting together. And most often when we talk about precipitation reactions, they are going to be double replacement reactions, which we talked about in regular chemistry. If you remember, a double replacement reaction, I always talk about it like if you think about 2 people dancing and then 2 other people dancing, it's like a partner swapity-doo. And so what ends up happening is that depending on your, I guess, perspective, your cations switch positions or your anions switch positions, whichever it is easier for you to think about. So if you think about, in this case, A starting off being paired with B, A then switches positions with C, and then they become partners with D, and C becomes partners with B. Okay, we'll go through an example and it'll hopefully make a little more sense. Okay. When you are figuring out your double replacement reactions, the most important thing that people do is they don't pay attention to the oxidation numbers, and that's critical. So you need to pay attention to the oxidation numbers so that you can write the correct formulas. Subscripts are not necessarily as important when we figure those things out unless they are for a polyatomic ion. So in this example here, if we talk about calculating, I keep saying calculating, but it's actually just figuring out a double replacement reaction. What I need to do is first, I need to pay attention to oxidation numbers for the chemicals that are reacting. So in this case, the ammonium ion that I have here has a +1, and that's what we're going to figure out first. The phosphate has a -3. How many we have of each of them is not as important as their oxidation numbers when we get started. We will deal with the incorrect quantity when we balance our equation, but you got to get the formula right for that. The same thing with the barium and the nitrate. Barium is a +2 and nitrate is a -1. So if you look here, all we care about is the formula for each ion and the oxidation number first. Then what we'll do is we will switch them and then make new partners and then deal with the balancing. So I'm going to walk you through the steps for an example, and then we will do a little bit of practice as well. So the first thing you have to do with these is you need to determine the oxidation numbers of each ion in the reactant. So looking at our periodic table, you can figure out that sodium is a +1, Sulfide is a -2, hydrogen is a +1, and chloride is a -1. These oxidation numbers in double replacement reactions do not change. In single replacement reactions, they do change, and that's something that we'll deal with later. But right now, double replacement reactions, your oxidation numbers generally stay the same. Okay. Then what you need to do is you need to switch your dancing partners. So in this case, I'm going to switch my cations out. I'm going to put the hydrogen with the sulfur and the Na with the Cl, the chloride ion there. And then we balance oxidation numbers to get the right formula. So I'm going to go back here for a second. Even though there's only one H in the formula for my reactant, I need to make the formula for hydrogen and sulfur work. So I'm going to put a 2 for my subscript for hydrogen. And in my previous one, I had 2 NAs, but when I talk about oxidation numbers coming together, Na and Cl are each a plus and a -1, so they work out, and I don't need the 2 there. So I don't care that I don't have those subscripts there. If this were a polyatomic, you have to bring the subscript for the polyatomic, but you don't have to bring the number of polyatomics along. So again, deal with the formulas and the oxidation numbers, and then the next step is going to be the balancing, and that's how we take care of the odd number that we don't have figured out. So if we look here, I've got Na2S, and I made NaCl, so to take care of the fact that I don't have the 2 NAs that I do on the left-hand side, I'm going to put a coefficient over here. Do not jam the 2 into this formula. It goes out front. NaCl is good for its oxidation numbers, so then I got to put the 2 out front to deal with that quantity. In the same kind of vein, the Cl now, I've got 2 of them, so I'm going to put a 2 here, and that takes care of the fact that I had to add an extra hydrogen to make my S work. Okay. Then what we do is we take our solubility rules and we apply them to the equation to figure out if we get a precipitate or not. So this is kind of like this laborious process. You get your double replacement equation and then you apply the rules. So if we look at the rules for Na and S, there's a rule about Na, it's an alkali metal. Alkali metals are soluble. There is technically a rule about the sulfides, and sulfides usually aren't soluble, but it doesn't really matter because it's got the Na in it, so that's going to be solid or soluble. So we're going to write that as aqueous. The same thing for HCl. Most chlorides are soluble, and hydrogen is in the alkali metal category, even though it's not a metal, so that's going to be aqueous as well. Oops, excuse me. If we look at our products here, we are going to have NaCl, Na, aqueous, that's good to go. H acts like an alkali metal, so that's also going to be aqueous as well. If you find something that comes out insoluble, you are going to write that as a solid here in this little phase area that we have. Okay, so here is an example that I would like you to try. I would like you to try to predict the following double replacement reaction. It's PbNO32 plus Ki, and I even gave you the 2 there. I guess I gave you a little hint. What I want you to do is I want you to tell me what my products are going to be and then whether or not I'm going to get a precipitate to give me the phases as well. So pause the video, see if you can figure this out. Again, first thing, find your oxidation numbers for everything. Then do this partner swap, the cation swap. Then balance your equation. Then check your solubility rules. Okay? Give it a shot, and we'll see how it goes. Okay, we're going to start here. If you look on your periodic table, when you find lead, lead is listed in the same chemical family as carbon is. However, lead and tin act like transition metals, even though they're technically not in there. And you say to yourself, Adi Meyer, how do I know that? If you look at this chemical formula here, you should know that the nitrate polyatomic has a -1 oxidation number, and it only takes 2 nitrates to cancel out the 1 lead. So in this case, my lead's oxidation number should be a +2, and nitrate is a -1. Potassium is a +1, and iodine is a -1. So what we're going to do is we're going to do a little swap, and when we do that, you get Pb together with I, and K together with NO3. Checking our formulas. Lead is a +2. Iodine is a -1. So my formula is going to be PbI2. K is a +1. NO3 is a -1. That formula is good to go. I don't care that there's a 2 here yet because my formula is the most important part. Then I balance my equation. So I've got 2 nitrates here. To show that I have 2 nitrates in my balanced equation, I'm going to put a coefficient of 2 in front of my potassium. The same thing for dealing with my iodine and now my 2 potassium. I'm going to put a coefficient here. Okay? Then check your phases. So in this case, lead, there's not a rule about lead. We do see it causing solids sometimes, but it's with nitrate, and nitrate is like our first rule. So if it's got a nitrate in it, it's going to be soluble. Okay. If we look here, K is an alkali metal, so that makes this compound soluble. If we look here now, though, PbI2, no rule about lead, but there is a rule about an iodide, and most iodides are soluble unless they're with silver, lead, or mercury. So since this is one of those exceptions, we are going to have to say that this is going to be a solid. And then we've got potassium nitrate again, which is aqueous because of the potassium and the nitrate. So here's just a picture of what's going to happen. When you mix these two things together, they are going to form a precipitate. And the precipitate is going to be our solid that you see here. And in the case of this beaker, it's going to be solid lead iodide at the bottom, which takes this kind of cool yellowish color. Okay, so this is what you're going to be doing for the first part of your homework. You're going to be working on these double replacement reactions, and then we'll get into talking about net ionic equations and how to draw particle diagrams next. Okay, if you have any questions, please make sure you get that cleared up, and good luck.